So what I want to do now is I want to cover something which constitutes quite a big part of high school organic chemistry, and is something that we very much assume that you know when you come to do 191 because we don't teach it at all. Right? So you do kind of need to have your head around this. Not for really hard molecules, but the basic ideas you need to kind of understand. So, organic nomenclature is the systematic way that we have to name organic molecules. Right? In fact, you can use it for systematically naming inorganic molecules as well, but we almost never teach you that anywhere. We just expect you to pick it up as we go along. But the organic nomenclature is a bit more important, apparently. So, we need to be able to distinguish one particular organic molecule from another. Sounds reasonable enough, because they all tend to be white solids. You can't say, I want the red thing, because they're not red, they're white, always, almost. So, for example, the food that you may buy says that it contains sugar, and oftentimes it will. It'll say it contains sugar. Fruit juice always contains sugar. But sugar isn't really a proper chemical name, because sugar could mean one of a whole bunch of different molecules. Right? Sugar is kind of like a class of molecule. And there's lots of molecules within that class. So sugar's not really any good. If we're chemists and we're all about knowing exactly what we're talking about, we need to have a way of saying it's this type of sugar rather than this type of sugar. And so there's this whole system that's been developed which enables us to systematically name any particular organic molecule. And in fact, one of the guys from Canterbury who was at the meeting yesterday is on what's called the IUPAC Nomenclature Committee. And so he and a bunch of other people have meetings in London twice a year to talk about new and improved ways to name molecules, if you believe. What we're going to find, and this is kind of outlined on the other side of your handout, so one side's got all those functional groups we talked about, and on the other side there's kind of an outline of how you go about doing this naming thing. And the naming thing is based on three parts. So any particular organic molecule that you come across, the name is going to be in three parts. Part of that name is going to be telling you about what sort of functional group it's got. Right, remember, and that's important because that enables you to know what class of molecule it is. So part of the name is about the functional group. Part of the name is about how many carbon atoms there are in the framework of your molecule. And then part of the name is about the way in which those carbons in the framework are arranged. The fourth part of the name is telling you about any other stuff that might be attached to the molecule. Right? So a bit that tells you about the functional group, that tells you what sort of class the molecule's in. We have a bit that tells you about how many carbons are in the framework. We have a bit that tells you how those carbons are arranged. And then finally we have a bit that tells you about anything else that might be hanging off around the edges. Okay? So what I'm going to propose to do is that we just go through some examples for a little bit, just showing you how the system works. We're not going to do great in-depth complicated ones. I think there's a few curlier ones in the tutorial, but you can name those based on these basic ideas, hopefully. Yeah? Okay? So here's a straightforward little molecule. This is an alcohol. You would know that because you recognize the functional group. Right? It's a carbon with an OH group attached to it. Nothing else, no carbonyl groups or anything. So this is an alcohol. And so what we do is we start by writing something called the class suffix. We recognize that the functional group is an alcohol, and so the class suffix for that is ol, O-L. And that goes at the end of the name, yeah, like a suffix. That's kind of an English word from somewhere at school. It means the bit that goes at the end of the name. And that's going to be the case for any alcohol. The end of the name is going to end in O-L. That tells you that it's in what sort of functional group it's got. Then we worry about how many carbons there are. There's 2 carbons in the framework of this molecule. And so then we have this wee bit of name that tells us about the fact that it's got 2 carbons. And we looked at this a little bit before morning tea. We saw that this is called F. Right? So ETH is a little part of the word, of the name, which tells you that there's 2 carbons in this chain of carbons that forms the framework of the molecule. right? And then the third bit of the name requires you to look at the structure and say, are there any double or triple bonds in here? Are there any carbon-carbon double bonds, which there would be if it was an alkene? Or are there any carbon-carbon triple bonds, which is what you would have if it was an alkyne? And in general, the answer here is going to be no for the molecules that you're most likely to see this year. Right? If it's no, then there's something called the hydrocarbon stem, which basically means the little bit of the name that goes in the middle of the other two parts when we name our molecule. And if you've only got carbon-carbon single bonds, then the hydrocarbon stem is just AN. So and then in this molecule, there's no stuff dangling off around the outside, so it's just these three bits that we care about. And so we put these together like this. So there's no substituents, that means the stuff dangling off around the outside. We'll see examples where there is shortly. And so what we end up is with these three parts, which we put together like this. F, the bit that tells you about how many carbons in your long chain, goes first. The an, the bit that tells you that there's no double or triple bonds in there, goes in the middle. And then the ol, the bit that tells you that it's an alcohol, goes at the end. And so you have F and ol. Yeah? And so this is kind of the way in general they all work. All the names have got, except unless you've got substituents out the front, and they get named out the front of it, then they all tend to work kind of this way. Kind of like with three syllables, like F and ol. You have an F or a prop or a but, which tells you about how many carbons you've got in your framework chain. The an, normally in the middle, and then the ol at the end, which tells you about the functional group. Okay. We happy with this? Yeah? Here's another one. Now this is what, remember from what we said before, this is an alkyl bromide, is the class. And there's two different ways you can approach this, but the way that we do it here is rather than calling this butyl bromide, which may be something you've seen before, we're going to name it the other way. And so to name it as the other way, what that means is that we name the bromine as a substituent. So for alkyl halides, the suffix at the end of the name is just an E. So it doesn't tell you in the suffix part of the word whether it's a bromine or a fluorine or a chlorine or whatever in your alkyl halide. We name that part of it in a different part of the name. Well, we specify that part of it in a different part of the name. Yeah. So for these ones, the class suffix is just E. Then we go to our number of carbon atoms in our framework, and our longest chain of carbon atoms in our framework, and we see that there's 4 carbons there, all in a row. And so the little bit of name that goes with 4 carbons is but. We look for any carbon-carbon double bonds or carbon-carbon triple bonds, and there's none here. So that means the middle part of the name is just AN, as it was before. And so just on the strength of these 3 bits, if we just went with what we had before, we would call this butane, right? But-an-e, butane. But of course it's not butane because butane has only got carbons and hydrogens in it. There's nothing in the name butane to tell us that there's a bromine there. And so what we do is we name the bromine as a substituent, which means that the bit of the name that refers to the bromine goes out the front. Yeah? So when we say substituents, the answer here is yes. And so the prefix, which is the bit at the front of the name that talks about the substituents, that's where we talk about the bromine. And so for a bromine, the way we name that is we put in the bit bromo. Yeah? We don't go bromine butane, we call it bromobutane. Hello. See, I so knew you were going to say that. I so knew someone was going to. The answer is no. In a little bit, we're going to get on to this business about isomers. But hopefully, to sort of jump ahead, if you look at that structure, you can kind of see that you can have the bromine on that N carbon, but you could also have a molecule where that bromine was on, say, the carbon that's numbered number 2, and that would be a different molecule. Yeah? If you put the bromine on the carbon numbered 4, that would be the same as this one. You've still got a long chain of 4 carbons with a bromine on the end. But if you hung the bromine off one of the middle ones, that would be a different molecule. It would have different chemical properties, etc., etc. And so we have to have a way of distinguishing that molecule from this one. And the way that we would do that is in front of the bromo part is we would put a number to specify which carbon in the chain it's attached to. Right? So in theory, you could have 1 bromobutane, or you could have 2 bromobutane, depending on whether that bromine is on carbon number 1 or carbon number 2. If there's no number, then you assume that that means 1. Right? So if we just wrote bromobutane, then the assumption is that the bromine's on the end of your carbon chain. If it was on one of the middle carbons, then you would need to specify which of the middle carbons in the name. Yeah?
What if there were 2 bromines?
I think there's an example like that coming, but if there were 2 on the end, then you would call that dibromobutane. There's another whole set of little prefixes, di, tri, tetra, penta, referring to how many of a particular substituent you have. Yeah? And?
So what's like chlorine and fluorine?
Fluoro for fluorine, chloro for chlorine, bromo for bromine, iodo for iodine. Yeah? Okay, what's next? Okay, so here's another one. So we look at this molecule and we go, what sort of functional group does it have? And we hopefully recognize that this is a carboxylic acid. The functional group for a carboxylic acid is COOH, and the suffix that goes with that is oic acid. So the bit that goes on the end of the name is something OIC acid. So we can do our same thing again. We can say, what is the number of carbon atoms in the longest chain of our framework, of our backbone? Here it's 2. We count the carbon that's part of the functional group. So there's 2 carbons here. So that would be F again. Are there double or triple carbon bonds? And the answer is no. Again, there's a carbon-oxygen double bond, but there's no carbon-carbon double bonds. And so again, the name is AN in the middle. And so there's some substituents. No, nothing else hanging off. And so the name for this one is F-an-oic acid. Okay, so generally they kind of tend to work like this. They can get desperately hard and complicated if you want, but they don't tend to. And to be fair, these days there's actually computer programs where you can draw the molecule, push a button, and it'll give you the name, or give you the name for you. So that's easier, but you don't get to play with those in first year. So now here's a slightly different one. Because now the carbons in the framework aren't all in a single row, right? They're branched. So we have to allow for that in our name as well. So first of all, what's the functional group? You've got a carbonyl group at the top there, which has got a carbon on one side and an H on the other. So that makes this an aldehyde. And the class suffix for aldehydes is AL, al. So that's going to be what goes at the end of your name. And then we come to this business about the number of carbon atoms in the longest chain. In all the examples we've seen up till now, all the carbons have been in a row. So the number of carbons in the framework is the same as the number of carbons in the longest chain, as we call it. But here it's a bit different. Now we've got 4 carbons, but they're not all in a single row. So what we have to do next is we have to find the longest chain of carbon atoms, and we use that to work out the next bit of our name. Right? So Oh, I don't have any numbers on it. I have to use my stick. So what we do is the longest chain has to include the functional group. So we have to start with this carbon here. And so we can see we can go 1, 2, 3, or we could go 1, 2, round the corner, 3. You can go round the corners. That's completely fine. And that's the sort of thing that we will do to try and catch you. We'll draw the molecule going around corners. Right? Remember, this is just a two-dimensional representation of what the molecule is. This isn't in any way telling you anything about the shape, the three-dimensional shape. Right? So going around corners doesn't really mean anything. So, but either way, 1, 2, 3, or 1, 2, 3, we can say that the longest chain of carbon atoms in the framework of our molecule is 3 carbons long. And so the next bit of the name then comes from that. So it's going to be prop, which is the little bit of word that means 3 carbons. Right? Carbon-carbon double bonds, carbon-carbon triple bonds, there's none. So again, the middle part of the name is just AN. And now finally, substituents, yes. The substituent now is going to be the other carbon atom, the one that isn't in our long chain, but we need to talk about in our name, otherwise we're not going to be naming this molecule. Right? So what we've got, I can't remember what's next. Let's say we go 1, 2, 3 across here. Then what we've got down here is a CH3 group, which is going to be our substituent. If the substituent is a CH3 group, then we call it a methyl group, which kind of comes from methane, yeah? So a methyl group. And in this case, this methyl group is attached to carbon number 2 in our chain. And so our substituent we could put here would be 2-methyl. Yes? Do you need to say it when it's there?
Because if it was anywhere else.
It would be a different molecule. Thank you very much. Yes, I'm just trying to make a point, I think. But you're right. What my friend here is rightly pointing out is, in fact, you don't need the 2 because there's nowhere else where you could put that CH3 group and for it to still be a substituted propanal. Right? If you stuck it on the end, then your long chain would suddenly be 4 carbons long. And it would be what? Butanal. If you put the carbon on carbon number 1, the methyl group on carbon number 1 instead, what would you have? You would have the end of the universe as we know it, because that carbon number 1 would have 5 bonds, and that would be wrong. Yeah? So it can only be there if it's a substituted propanal. So in this case, that 2 is maybe a little bit redundant, but I'm making a point. Yeah. So the name here, you could call it, would be 2-methylpropanal, or just methylpropanal if you wanted. Now note that the number is separated from the substituent by a wee hyphen. That's a standard thing. But this substituent is separated from the rest of the name just by a space. So it's not all one word. You've got the substituents and then a space and then the rest of the name after that. Yep.
Does the number always start from the functional group?
Yes. The number always starts from the functional group. Maybe one more that I should mention briefly is if you have this, that molecule, yeah? With my little shorthand cartoon thing. So this molecule is going to be some sort of ane, yeah? Because it's got no functional groups at all, so the end of it is just going to be E, yeah? No carbon double bonds or triple bonds in here, so it's going to be AN in the middle. Then we have to know how many carbons are in our longest chain. How many carbons are in the longest chain? 6. 1, 2, 3, 4, 5, 6. Hex, indeed. So it's a hexane. But then that name doesn't allow for this little methyl group that's hanging off the side. Right? Sorry? 3-methyl. Why do you say 3-methyl? The closest to what? from the closest end.
You number them,
You do.
and whatever one is the smallest number, you use that.
Fantastic. There is two different ways that you could number this long chain of molecules, of carbons, right? You could go 1, 2, 3, 4, 5, 6, or you could go 1, 2, 3, 4, 5, 6. If you start at this end, then you would say that the methyl group is on carbon number 4. If you start at this end, then you would say that the methyl group's on carbon number 3. And the rule is that you always number it so that the substituent has the smallest number if it has options. Right? So that would make that one 3-methyl hexane, not 4-methyl. It's getting a bit subtle, but nonetheless, this is another one of the rules you're likely to come across. Right? So you always try and do the numbers so that it's the smallest. And I suppose what if we did that? If we had that molecule now, which had a CH3 group here and a CH3 group there, how would we name that? 2,3, there's like an echo in here. 2,3-dimethyl, right? So now 2, 3 hyphen dimethyl. Two numbers now because you've got two methyl groups, but they're on different carbons. So the numbers here specify which carbons they're attached to. And then you have dimethyl telling you that there's two methyl substituents. Right? So the number of numbers here kind of has to match up with whatever you're putting here. You can't have 2,3-methyl cyclohexane. That doesn't work. Yeah?
If they're both on the same one, do we have to say 2,2
Yes.
dimethyl?
Yes, otherwise it could be this instead.
So we couldn't say just 2 dimethyl?
No. If it's that, oh, no, it's not. No, let's not do that because that's a bit messy. If it's that molecule, then that would be 3,3-dimethyl hexane. You see how this works?